Okay, go ahead, Artem.
Okay, hello everyone. Today I will present a paper with the title Physics Informed Machine Learning with Heuristic Feedback Control Layer for Autonomous Vehicle Control. It was made in one of the Mitsubishi labs, I believe. Okay, and let's go. It's an outline. Okay, so nowadays autonomous driving involves it includes such things as cruise control, lane keeping, lane changing turns, and others. Automatic lane changing is actually not an easy problem because it requires both it requires both longitudinal and lateral control, and also trajectory planning. And usually, MPC is used to solve this problem. What is MPC? MPC is a model predictive control. It's a feedback control strategy that continuously solves a short planning problem. It is usually used in controlling the work of planes. And it takes input, the vector of states, the state vector. Then it tries to minimize a cost function by selecting an optimal sequence of moves.
Which variable here describes the state vector?
The state vector is xi, controlled variable. And y is a manipulated variable that we can change. And here it's just.
So that's misleading. You say controlled variable is not that you control?
Okay, we try to control this variable, but we cannot directly change it.
So that should not be called a controlled variable.
Okay, maybe.
Yeah, okay. So, and the manipulated variable is the one we can actually control, yes?
Yes.
Okay.
And then in the case of a car, controlled variable can be the position, the I don't know, speed,
velocity.
And velocity. Sorry, yeah, of course, velocity. And manipulated variable will be an angle steering angle, and like maybe acceleration. How much do you push the pedal?
Yeah, but what depends on the other? I don't here. The dependence of x on u is not shown, right?
Yeah, it's not shown here.
Okay.
And of course, there is dependence, and it's just.
What is the reference variable?
Reference variable. Okay. I will show you later.
Okay.
On one of the next slides. And this model of predictive control, it respects hard constraints that we can encode inside. But the disadvantages is that it has a high computational cost because on each step, a solver has to recalculate on each time step a solver has to recalculate the entire control sequence over the receding horizon. So solver tries to predict a sequence of steps, not just one step, but few steps in the future. But then the model will use only the first predicted step, and then the whole calculation has to be redone again. That's
Artem,
how
I'm
it is.
missing predicting of what?
Predicting of
There are variables here, R, X, U.
okay, changing delta U. We try to predict delta U.
Why do you want to predict it if U is something you change yourself? It's a manipulated variable. There's no need to predict.
Yeah, but you can change it yourself only if you're a driver. But we are speaking about autonomous driving, so we want it to be changed automatically.
Yes, and then presumably the model wants to predict not what it can change, but predict the behavior of the vehicle. So it want to predict this maybe controlled variables.
Well, no.
Or why would you want to
actually?
why would you want to predict the variables that you can change? It's the model, right?
But we want okay. We actually know what state do we want to get in the end. For example, we want a car to change its line, and so we know
What is the variable that what is the variable that describes to where you want to get?
Okay, it's not here on this slide. It will be later. There will be actual variables that describe the position of the car, velocity, etc. Here, I just wanted to give you a quick description of the model predictive control.
But hold on. You already told us that everything is here. You said that position and velocity are the controlled variables.
Okay, not on this slide. It can be incorporated in control variable, but it's not here. Okay, maybe.
How about this? How about this? There are three types of variable. One variable is where the vehicle is or will be. The other variable is where you want the vehicle to be. And the third variable is the thing that you manipulate. So all three variables are here. I just don't know which name is what.
Okay, so let's talk maybe about position of a car. So the current position is controlled. The variable desired position will be the reference variable, and the change in steering angle will be manipulated variable.
Okay, so everything is here. Great.
So the second term is like the cost of controlling the car or something like that,
yes,
and the first one it's okay.
Yes, that's
you may not be able to steer a wheel too quickly or something like that.
Yeah, okay, get it.
And here is just an example of an MPC function, and it is not directly related to autonomous driving. I will show you the real.
But then controlled variables. Yeah, so then controlled variables actually are controlled variables, and they should depend on the manipulated variables. So it's where the car ended up, given that you rotated the wheel. So then they are controlled variables. They're not directly controlled variables. They are variables. They are functions of manipulated variables. That's what it should be.
What I want to explicitly mention is that neural networks are not used here in model predictive control. Solver just solves optimization problem.
Mm-hmm.
And next is approximate MPC. It's an idea to decrease the calculation cost. So instead of solving the full problem with a solver, we can train a neural network. So we may create a data set from the solutions of usual MPC. Then we can use supervised learning and with a simple feed-forward neural network. So it will forward passes. They're usually less costly than using a solver. But the problem is that this approach heavily relies on labeled data from the MPC solver. And so there might be cases that just didn't get in your training data. And during these scenarios, AMPC will have problems. So it's not actually good for autonomous driving. The next thing is differentiable predictive control. It's an idea. So let's make the entire MPC calculation graph differentiable. So we can
I don't understand what is the which graph we're talking about here. MPC looked like an equation which has function of three variables. I don't even understand how I can solve it. It's just a function of three variables, x, r, and u.
Yeah, but now imagine a neural network that you train. You have an input, you have an output, and
what is input?
Output is a solution of usual MPC.
I don't understand the solution of usual MPC. I don't understand what you're solving for.
Let's start again. So here
this is an equation. So if you want to solve it, you need to solve for what?
Yes, you solve for example, delta u. You can solve for delta u or for u simply.
So you solve for u, okay,
yes.
But what are you given?
You're giving xi.
You're given xi and ri.
Yes, yes.
Okay, if I given xi and ri, I plug them in, I add them up, I get a number. And then I have only one equation for many u's. I cannot solve it. There are too many u's.
No, of course, you have other equations that are responsible for relations between xi and ui.
But again, then I'm not understanding what
here.
I'm solving for.
You're solving a minimization problem. You're trying to minimize this cost function.
Okay, so let's assume that xi is a function of ui. Yes? And you are trying to minimize. If xi is a function of ui, that then starts making sense. Okay, xi is a function of ui, and you're trying to solve for ui's which minimize it. Yes, that's the idea.
Yes.
Okay. All right. So let's say I solve it.
And let's say you solved it by using a solver, and then you can like make multiple training data with these solutions, and then you can train a neural network. And
Why do you
this
need
is
to train a neural network if you already solved for you? Or maybe I'm not understanding what your neural network, what will be input and output for the neural network. That's what I'm missing.
Okay, we are trying to approximate the behavior of a solver, let's say, with some small neural network, because using solver is computationally expensive, but a feed-forward pass neural network is not so costly.
Sure. So what is it taken as input? What is it taken as output?
Input the same as here Ri and Xi, and output is Ui or delta Ui.
Cannot be Xi. That's what I'm trying to say. If you input the position, I understand, but you're saying that I'm inputting Xi, which is a function of Ui.
Okay.
So maybe you input the Ri, and then you want from that to get UIs. And then once you do this UIs, your vehicle will behave a certain way and it will produce Xi. Something like that. Okay, well, anyways, without having a picture, it's hard for me to understand.
Yeah, I understand. And later there will be
okay, maybe example will do.
equations.
Maybe example will help. Yeah.
Yeah, there will be an example.
Okay.
But later. So here the idea of AMPC is using neural network instead of solver, but trained on the solutions of solver. It's faster, but it relies on training data. Then differential data control. We are trying to design our neural network in a way so that everything is differentiable. Every calculation. And here it is, we want this to make the training unsupervised. And if we can do this, then we can apply physics-informed training that uses actual current model instead of the training data. So we can plug we can plug physical constraints into loss function.
Yeah, Artem, without examples, it's hard to understand what all those words mean, seriously. I mean, can we just get to the
Okay, yeah.
Yeah, because it's just some, yeah, go ahead.
Okay, but I will have to say one more thing, is that during
I don't even have a picture what this feed-forward network is. I don't have an equation showing here's the output, here's input. And that's why all those words are just words for me without clear interpretations what they mean. I mean, it would be nice to have a simple example, perhaps, or in general example, which would show exactly what those words mean. What's the input, what the output, what the training. Okay, maybe this will help. I don't know.
Okay. Okay, let's maybe start with the problem statement, and here non-linear bicycle model is used as a simple model. So here we have x, y, they are ground coordinates, and x, y small, these are vehicle coordinates. There are velocities. There is an angle, your angle, and there is your rate, omega, and it's just a model. It can be derived, but I thought that the derivation of this model is not actually the main point.
This is just physics, right? So we make an approximation of how the system behaves, and you write down equations.
Yes.
So this is physics.
Yeah, this is physics. It is possible to show how all these equations are derived, but so here, okay, let me find for you. Okay, here is the cost function that was used.
I didn't see any use on the previous slide. What is the use on the previous slide?
Okay, U is not here, but let me actually find it. Yeah, I think it's simply not on the slide, but U is actually a vector consisting of two variables. The first one is A, longitudinal acceleration, and the second one is, okay, the first one is A. Can you see my pointer?
Mm.
This is the first coordinate, and the second one is delta F, which is front wheel steer angle.
Okay.
So these are two variables that you can directly manipulate, and two components of U vector. This one. So this is the loss function that we try to minimize. U is a sequence of UKs where K is a time step. So K0 is a 0 time step, K1 first time step, second time step until P minus 1. So the model predicts a sequence of UKs, not just the first UK. But this is how it works. And xref is a reference state vector. The first coordinate.
What is QE? What is QU?
QU, big Q, QX, QU, QT are actually matrices with fixed entries that are not trained, not optimized. These are weights.
That's the input part, right?
No, they are supposed to tell you how hard it is to accelerate or how hard it is to turn a wheel. So that's what QU should.
In case of QU, yes, this is a like punishment for changing.
And again, what's
something.
missing is X is a function of U. So it has to be written explicitly because otherwise this minimization problem is trivial.
Okay, so the dependence is presented here. So as I said, A and delta F are components of U, and
it's not written
velocities.
Here. It's not written here. So X and Y are positions. Equations for X and Y are not written here. But once you write down equation for X and Y, you will see that they're functions of A and delta F.
Well, here they are written in differential form, but
yeah, but that's not what you are putting in the loss function. You're not putting V's, you're not putting V dots, you're putting X and Y. X and Y are functions of all those variables that you have here. And X and Y will go, most importantly, they are functions of A and delta F, which I use. And so then you can really do this minimization problem and find U's or A and delta F, which minimize the loss function. And moreover, capital X down there is small x here. I don't know why you're switching notations, but
no. Well, small x is a state vector. It has different components. The first component is y, vertical coordinate. Like the second component is phi, or it's not phi, it's maybe c or CO angle. And the third component is longitudinal velocity, then lateral velocity, and the fifth component is yaw rate. Unfortunately, I simply forgot to write it down on the slide.
But okay, so x, small x is a collection of some of the variables on this slide.
Mm-hmm.
Fine.
Yes.
And okay, fine.
And so when a car changes line,
no, that's a reference. I'm saying there is also xk, which is not the reference, but the actual behavior of the car.
Yeah, of course. xk is an actual state of a car.
The definition of x, small x, is missing anyways here.
Yeah, here on this slide it is missing.
Yeah, it's missing.
I agree. And it's because I simply forgot to add it.
Both x and u should be nice to have both x and u here.
Yes, I really agree here. And also some constraints on components of u can be applied.
Yeah.
So for example, we don't want steering angle to be maybe too small or too big. Okay. Next, here I have to return to the DPC, differential predictive control, where neural network is trained. And there, like one of the major contributions of the authors is that they moved from simple feed forward architecture of the network that predicts all all NP steps, future steps. They
the summation are the steps of the simulation. Sorry, that
Yeah,
was very confused
summation
about
is the
that.
step of the simulation. Yes.
Okay, so the whole.
Artem, we're running out of time. Can we move on like to the result? Like, what's the the main results that they have seen. Now we understand what is this.
Okay. So let's quickly move to the results. So authors incorporated what they call heuristic feedback control layer. So in usual approach, UK will be the output of the neural network here, but they actually use formula 4. They get UK as a product of a matrix to the vector, where the components of the K matrix is actually the output of a neural network. So they are not predicting
Why?
UK directly, they predict
Question
the
is why?
components of K. And they use a special form of K.
So the question why? Yeah.
Yeah. So the idea is to use Lyapunov function and to select to use some assumptions. So here, for example, they said that some errors are less important than others, so they may be simply excluded from the equations. And so that's why they used J1, J8 as 0. And then
why?
they also...
Why? So the question is...
It is heuristic. It's heuristic. They simply...
No. On the previous page, there is a very particular formula. So equation 4 with the matrix and the proposal that 5 it's very particular. There's squares and other things that appear.
Yes. So here
Why?
J1 is 0 and J8 is 0 because some of the errors are not important.
Why errors are related to this matrix? Why this matrix? So let's say I agree that some things are less important, some things are more important. Still, matrix K has a very particular form. So it's a 2 by 5. So 2 corresponds to the 2 controllable parameters, or manipulated parameters.
5 state parameters.
And 5 are the state parameters. And so I understand that x reference minus xk is, well, noise, your uncertainty in
yes.
You do not end up
where
you want it. Yeah, it's about error. So and then and after that I'm lost. So because I'm actually not sure I understand why in equation 5 you have index k on the right hand side and you have index k on the left hand side, and you have index I on the left hand side, but no index I on the right hand side. So then I don't understand. You cannot have indices appearing only one side unless they're summed over.
Because K refers to a particular time step. And so the output of a neural network, P, is a vector G. And this vector G has 8 components. So maybe...
No, look at equation 5. See equation 5?
Yeah, I see.
On the right-hand side, there's xk. And so k runs from 1 to 2. Okay? So there are 2 possible outputs, there are 2 possible values on the right-hand side. And on the left-hand side of equation 5, you have k runs from 1 to 2, and I runs from 1 to 5. So there are 10 possible and entries, elements on the left-hand side. So you cannot have that. So or you are assuming they all are the same. So, and then if you're assuming that all of them are the same, then you really need index I. So probably they're not.
Okay.
Actually, the second index runs from 1 to 8. Sorry, it's not 1 to 5. It's 1 to 8.
Yes, it's 1 to 8, and really you can just this notation is not really correct, but authors used that.
No, but you only have 2 possible variables on the right. Anyways, I don't understand the equation 5. I don't understand equation 4 either.
Do you want to say that I can be only 1 or 2?
No, I said K can be only 1 and 2.
But no, K is a time step.
It's not. It cannot be a time step according to equation 4. Equation 4, there are only 2 K's. K equal to, because U has only 2 components. Or no? Or are you saying U is... Okay, it's confusing.
Okay.
I don't understand what does U have 2 components or not?
You have 2 components, that's right.
Okay, does neural network produce 2 outputs then?
No. Well, usually in the case of equation 3, yes, there are 2 outputs, but the authors, they use different approach. They produce 8 outputs.
8 outputs. Okay, now it makes sense. So now, in order to this notation to be correct, all you had to do is had a subscript next to pi. So pi RPC subscript I. No, pi HF RPC subscript I. Then notation would make sense because it's a function. It's a function which it's 8 functions actually. It's a vector. Okay. Fine. So instead of using one neural network that produces directly the outputs, they have 8 neural networks that produces 8 outputs, and then some linear combination of them with the inputs gives you the actual value of controllable parameters in equation 4. Good. Okay. And so how does that help in the driving environment?
Good. They also used squares here and here because they said that they wanted the closed loop system to be Lyapunov stable. So they had some intuition about it. And well, the result is that the first picture training losses for HF RPC, the loss is less than for simple RPC. And the next picture is actually more interesting. It is the result of the simulations. So they used specialized software to run cars that used these different MPC, HFRPC to make decisions. And here are the trajectories of cars that were required to change the lane. And if they used AMPC, it's had 12 significant deviations. DPC and RPC worked better. They failed only in 1 cases, but their HFRPC achieved a 100 success rate in different scenarios. And these are their 2 main results of the paper.
Interesting. Okay, Good. So I guess my only problem, if you can go back to the architecture, which is equation 7, 4, whatever. Yeah. So this is just an architecture. It just tells you that instead of outputting two numbers as equation 3, because we know U has two parameters, you say first output 8 numbers as equation 5, then have some direct connections from the input to the output through equation 4, and linear combination with those 8 parameters will give you the right output. So there is some architecture that is.
Yes, there is some architecture,
Yeah.
and let me briefly show it to you.
Mm-hmm.
Okay.
Well, that's an algorithm. What I meant is you can really draw what this linear layer is, because it's not all it does is connects input to the output. Well, there is product, of course. Okay, maybe that's the interesting part. So it connects input to the output through the product and not through just summation. And because of that, they managed to get the loss down. Okay, interesting.
Yes, so this is the idea behind this.
Very good. Okay, are there any questions, comments? Right, sorry, I had to run later today, but yeah, so yeah, the main idea is equation in between 4 and 5. Well, 4, equation 4 is the main idea. And so if it would be nice to understand why this and not something else. Like, derive this equation from some assumptions about how the X reference or X case behave. Because then it would be kind of, you put some constraints on the architecture, which produces better result, which is always interesting. So where does it come from? Must come from something about the data. And what is it exactly that gives this shape to the architecture? It would be interesting to figure out. Okay, thank you, Artem. There are no questions. I'll see everyone next week. Thanks.